Well, here's a video for class 23. In actual class 23, we mostly did the Excel spreadsheet stuff, but I did want to include and expand upon the multi-pipe systems. So here is what we're going to cover this and hopefully get an example in. I think in class I said because we ran out of time, we're not going to do that third problem. I will change that shortly, but I'm going to leave it as a extra credit problem, and I want you to be able to do that. So I'm going to create at least one or two videos addressing this topic. Right. So multi-pipe systems. This is a useful concept to absorb because it also ties into analogies to electrical engineering and some other types of systems. It's kind of an interesting thing to see. All right, so if we have a pipe and it's changing diameter, let's say, in 3 positions, we could think of that as being like some series resistors, analogous to that, where we have between here and here a head loss. We call that head loss 1, maybe HL1, and then the head loss between here, HL2, and the head loss between here, HL3. So the total head loss that this thing's going to experience right here, H tot. That H tot is going to be equal to HL1 plus HL2 plus HL3. I mean, that's pretty understandable. Well, we could think of that as being analogous to a voltage drop across resistors, right? This head loss. And if that's voltage, you could guess what current it's going to be. It's great. It's going to be flow. They're calling it Q here. I'll leave it as Q. I think in class I used the V's. But you can go that Q1 is equal to Q2, which is equal to Q3, right? It just has to be the same. It's conservation of mass tells us that, with the density being constant right here. So you could think of this as being the current. And even the idea between current, right? Like current down a river, right? This is the current flowing through the thing. Now, analogous, we could have the parallel system. So like kind of like parallel resistors. And what we'll know here from this is that we can have the flow, the total flow into this system is going to be Q tot is going to be Q1 plus Q2 plus Q3. This, of course, is also analogous to current. And then we could say, well, we could take it on faith that the voltage drop between, not the voltage drop, but the head loss between here and here is going to be the same. We could prove that here in a second. We could say that HL1, that's across this guy right here, that's HL1, is equal to HL2, which is equal to HL3. So if you want to find how these things are related to each other, or how, if you have a problem and you want to solve it right here, these are the system of equations that you could set up to, with that mindset, to solve a more complex problem, right? Noting that I'm trying to remember the name. I'm losing it right here. One second. When you try to find a complex network, these are the concepts for the series versus the parallel that we'll use. One second. Yes, okay, I remember what it is. Is like analogous, I think I'm spelling that wrong, to the Kirchhoff voltage and current laws. But let's go ahead and prove this, because I think this is a sort of a hard one to digest. And so we have this one set up here for this, like we might call a loop system. You got to be careful because we don't know what necessarily in certain respects what direction like maybe a flow will go. So in this we've assumed a direction. But let's take a look at the path right here. And of course this is going to be in series between here and here, and then series between here and here, but these are in parallel. But we're still going to go from here up to B, and then from up here up to B, right? So we can go from either way. So let's take a look at what happens, and then kind of isolate, make the decision. Does the head loss across 2 equal the head loss across 3? That's our goal right here. So if we start off and do our Bernoulli between A and B, let's see, the way I wrote it, I didn't like the way I wrote it right here. I'm going to go PB, right? So this is going to be Bernoulli 2 divided by a gamma plus VB squared over 2G plus ZB, yeah, is equal to, and then I'll do it to A right here, right? So we'll say that we have PA over gamma plus VA squared over 2G plus ZA. And now we're going to minus L1 and then minus one right here. And we're going to go through this guy right here. Did I do that right? Yes, I think so. So what we really do, we go to A to B, but we're going through this branch, HL2. Now we can also do the same thing, but now we'll go through this path right there. So P, this is all, really going to be all the same thing. I don't know why we're writing this out here, but that's okay. We'll take care of it. It's the idea behind it. PA gamma plus VA2 squared over 2G plus ZA minus HL1, but now we have 8 minus HL3. If we go ahead and subtract this equation from that equation, of course, all these things are going to cancel out to each other. But what we're left with is a minus HL2 minus HL3 is equal to 0, right? Subtract one thing from another. And what we end up finding is HL2 is equal to HL3. So we've kind of done a little proof right there that actually happens. Now we're going to try, I think I can squeeze in for this, the other video here, the example. Maybe, I don't know if I want to make it separate, but anyway. So we might have like a 3 reservoir system, and this is what like the homework problem that's been assigned is related to. And I decided, I don't know, I guess I've made the decision that because the example that I have is much more complicated algebraically than the problem that I assigned as homework. So I've decided to change it to an extra credit problem instead. And we have a 3 reservoir system. We don't necessarily know. If we close these valves, let's close this valve right here. And we know chances are if A is higher than B, the flow is going to come down this way. But if we open up this valve, we're not 100% sure if the flow from here is going to go in that direction, or if this right here is going to cause this to come up to here, and flow is also going to, is the flow going to split from here and come down to there, or is the split going to join? So what happens right here in B is kind of in question. So when writing out the equations for this, we have to kind of like make a guess and ahead of time and see if we have the correct value for the direction. Notably, we can have a much more complicated network of things going on, and this is a real problem. This actually does happen, especially you could think of especially, a lot of times you don't want to have it just go into a single branch, because what if there's what if there's a network for fire hydrants in a city, and you don't want, just because you have a break down here, that it disables the entire thing. You want to have a different route to be able to come through there. Maybe you might accomplish that by having, valves that are shut, and have ways to isolate this thing off right there. So you could shut these valves, and then you can open up this one so you can continue to the other fire hydrants. But this is something that can occur in other situations and what we end up doing is we having node and loop equations, which are really the Kirchhoff voltage and the Kirchhoff current equations, right? So you could have something in at a node, which is the boy, I'm about to say it the wrong way. I think that's the current equation, right? Well, it should be the flow rate, right? And then you could have around a loop, which is the Kirchhoff voltage law, Kirchhoff voltage law, right? Let's see. Let's take a look at other analogies. So I will do another video for the example right here. So here you go. I put up some pictures. This is not a loop system right here, but it is a complex system. And one time, one project I worked on a high-speed ferry, we were modifying the design. It was done in another country, and we needed to have a sprinkler system on it per Coast Guard rules. And I wasn't going to touch that with a 10-foot pole. We hired an outside group that had software that could do and figure out the piping diameters and arrangements to get the proper coverage for the sprinkler system, and some of the equipment that's required to make sure that it goes off in the right way. And some of them have like compressed air inside it, so when a fire gets a high enough temperature, reaches here, that something melts or at least gets triggered inside the sprinkler, and then it goes off. You don't want to have water inside here like all the time ready to go, especially on a ship. Things corrode, and that's not a healthy way to do that. But anyway, it's a more complicated system than I felt comfortable doing. The people who have expertise in this and have the software, it's a better approach to take to things. So yeah, I think 12 minutes is long enough for this video. Just talking about the piping networks and one something closely related when we're talking about branches and networks is flushing the toilet and causing the shower to starve the cold water, so that the hot water, the ratio of hot water and cold water is large, or changes, I should say, and causes some burning of the person taking the shower nearby. Here's some analogies. Okay, so Dr. Osaki, my friend across the hall, suggested this book, Practical Electronics for Inventors. There's a bunch of different analogies. They extend this analogy between fluid flow and electrical flow here. So you can see it in a DC circuit right here, where we have like some type of power source to create pressure, and then the load is sort of like a filter or something that's causing a pressure drop, right? So there's high pressure and low pressure, and having the voltage, high voltage and low voltage. Here's one where we see some stuff in series and in parallel. So you can see what these different lights are at the different stages here along this battery, and you can see these voltages that at different levels onto the things. That's sort of an interesting analogy and picture to pick up. Where you look at the pressure as it's increasing down here. You can see where the voltage is increasing as it goes down there, and you can see the flow coming out in terms of the distance the stream is coming in each. And you can see that there's brightest in the light as we come up. So these are good analogies to try to capture and remember, because it helps when you have multiple ways to think about something, when you start to puzzle it out and start to be a problem solver. This goes on and on. where we have, okay, here's like a little hand pump thing right here where you're creating, so it's reciprocating. You can see this is a cam, and it's pushing this up right here. So this is two different, this is the same circuit right here, but now we've made an AC type of situation where we're changing from high pressure and low pressure to high pressure and low pressure here on the other side. So it's reversing. So we have that pressure being sort of like current changing. So the direction of the flow is changing as you rotate this handle, which is changing this cam. So there's another analogy. Continuing on, here's a capacitor, right? So we're kind of like, and so you can think of this as like a rubber diaphragm that's kind of getting charged as we and here's like a switch in the opening and the closing. So you can kind of see it's sort of storing water. So you can think of that as being like a capacitor. So this is like a water capacitor, and the displacement current. So it's charging, and here's uncharged. We also have a diode. I thought that was a pretty interesting. This is more like this closing of this valve, right? So it's a check valve type of idea where it can flow in one direction, but it can't flow in the other direction. So here's the example that I was going to bring up, and I'll do that in another video, and we'll see how to solve it. Algebraically, this is sort of a pain in the tuchus. You'll see, though, how it gets done. So that's it for this video.